Hi, I'm Ariel Levkovich from NVIDIA.
And hi, I'm Marcelo from Red Hat.
Today we're going to talk about OVN hardware offload. We're going to do a quick overview of why is it needed, the challenges and work we did in order to achieve full offload, show them some performance numbers, and talk about the next steps. So let's get into it. Why is it needed? So as cloud environments getting more and more bandwidth demanding, networking performance demanding with the new speeds of 200 and 400 gigs around the corner, and more complex applications such as AI, machine learning. And in addition, we also see more and more new networking features in the field of security, quality of service, and more. As they are introduced, it creates more and more complex packet forwarding paths, and the SDN enforcement by the CPU becomes more and more heavy, where the CPU needs to invest more time in the packet forwarding. Just as an example, you see here the data path rules for basic east-to-west traffic with OVN Kubernetes deployment. We see some rules that basically using all the possible different features, such as connection tracking, Geneve tunneling, VLAN push and pop, and in the reverse direction, we see all those actions being used again in the reverse order. Here in a graphic display, we see the same data path a little bit clearer, where the packets from the VF are undergoing at least 3 rules where they are being matched on, undergoing connection tracking, encapsulated with the tunnel header, forwarded between the underlay interface to the overlay interface, the VTF0, and essentially are forwarded to the wire. And again, this is just in one direction, and relatively simple use case of east-west traffic, while there are other use cases that sometimes introduce 3 or 4 connection tracking actions in a single direction that also involve NATing. And as I mentioned before, this stuff becomes very heavy and overloading the CPU. So joint effort by Red Hat and NVIDIA teamed up to take a look at how can we get all those various data paths and use cases to be fully offloaded. We worked together to review and map all the different use cases and traffic paths that we have today in OVN-based cloud environment. And we put them under test. And as we went over the different use cases, we discovered that things sometimes are not that pretty, and we are not able to get the path fully offloaded. And so we started to work together to resolve those issues, to close the gaps and fix the bugs. And sometimes we even just put a little effort just in order to optimize data paths in order to achieve better performance, not only when using hardware offload, but sometimes we even discovered optimizations that can actually benefit the software data path itself. In this joint effort, we didn't only take the common approach where we fix and adjust the lower layers, which are the offload driver, the offload framework in the kernel, to the demands, requirements, and current implementation of the upper layers. But in this case, we often saw the need of changing the upper layers based on the constraints of the lower layers and the offload layers. So we'll see later on, and when we go over the things we did, that many times we just changed and worked on the OVN itself, the OVN orchestration layer, to adjust it, either to optimize it or to fix it to work according to the hardware offload constraints. So we're going to go over some of the stuff we did, different areas we handled in order to get to full hardware offload. And one of the major things that we had to work on is the feature that is heavily used by OVN, and it is connection tracking. Connection tracking offload itself already exists, and joint effort in the past achieved pretty massive feature that comes across different layers from the driver itself all the way up to OVS and in the TC layers in between. As a standalone feature, which is already obviously upstream, this connection tracking is known to be working, but we discovered that once put together with complex orchestrations and data paths and coupled together with sometimes other actions, we are facing new gaps that we had to address and resolve. On top of the connection tracking offload itself, obviously we got other layers of OVN Kubernetes, OpenStack, depends on the OVN orchestration layer. And each and every one of them, when put together under test together with connection tracking, creates different usage of connection tracking, and putting it under test help us to unveil different gaps and missing parts that didn't allow us to get a full offload of the data path. So obviously we had to change and address those components again. One of the first things that we encountered and had to handle is matching on the city state. So the kernel TC offload of connection tracking and the OVS weren't really compatible in that aspect. As TC offload for connection tracking first was introduced with the three basic states, tracked, new, and established, it didn't support the additional states of related, invalid, and reply. And we discovered that OVN is actually using those flags quite a lot in the data path. What we had to do is to make sure both layers are compatible. So first, we had to address it in OVS, which was actually ignoring those flags from the original rule when offloading it to hardware, to the TC layer. And on the other end, TC itself wasn't supporting those flags at all and was ignoring them. This led to incorrect rule in the TC layer, incorrect matching that variated from the original rule that OVS had it planned. So in OVS, we added support for offloading those flags, while in TC, we added some code to address those flags and make sure they are addressed. And in addition, to make sure OVS is compatible with the kernel, we add a probing method to OVS in order to make sure and query the kernel to see whether which flags it supports and which one it doesn't. And only if the kernel supports all the required flags in the rule, OVS will offload it to kernel. One more item, the next one we have to handle is connection tracking, TC connection tracking together with IP fragments. So connection tracking will not handle fragments, and it will reassemble all the parts into one big packet before performing the connection tracking action. Once this is done, we get quite a large packet, and it may occur that the forwarding device has a lower MTU than the new packet that was reassembled. This creates a problem, and in order to address it, a patch was introduced to resolve this issue and add a hook to the packet that once the packet is completing the CT action, it can be fragmented again back to the original fragments and avoid this case where it can cross and forward it to interface with a lower MTU. The change is contained and is making sure that this functionality exists only if the ActCT module itself is loaded in order not to hurt performance when CT is not used. And to continue from here, I'm going to hand it over to my colleague Marcelo.
Thank you, Ariel. The next one is TC and CT in Zone 0. Zone 0 is special because it is the default one for the system. So it's not just for TC and CT, and it's usually not used again later on. So the applications usually jump to a different zone and or to yet another different one, but doesn't go back. And the OVN Kubernetes actually does it. It goes back to zone 0 in the middle of the pipeline. And took us a while to notice that the zones, they were confused, and then to understand why that was happening. It was because the TC-CT action wasn't setting the template in such case. So OVS was asking for it to go back to zone 0, but it wasn't. And debugging OVS data path is quite hard. This bug would be hard to find on TC software data path as well, even if we let the hardware part out, or even with OVS kernel data path. On next one, TC, CT, and OVS. So TC, when using CT, it requires that the driver restores the last executed chain ID in case it triggers a miss. That is because it is replicating the same behavior that the OVS kernel data path has when it's on a different recirculation ID and then a miss was triggered. The vSwitch needs to know on which recirculation ID that happened. And this is not too different from when the TC data path is being used. Well, OVS supported this since day 0, or when using TC and CT, but only when using the ingress queue disk. Then the flooding of internal ports wasn't an initial plan for the CT. It was developed upstream by another vendor, Netromon. And in the end, it turns out that it became a gap for OVN because OVN uses CT on internal ports as well. And then for the egress, or on these ports, it wasn't restoring the chain ID. So that led to some flows being executed twice on the same packet, and some matches that should be doing that they weren't doing because some operations were already done. It created quite some chaos in there. And these are the fixes that we had on this context. So the first one, the restoration. The second one, and the third one is about scrubbing metadata from the packet when switching from a direction from ingress to egress, and then from egress to ingress, some metadata needs to be cleared. TC River uses to rely on the SKB packet scrub, but here we're not crossing network namespaces, so that didn't apply. And TC and OVN, TC was mainly used on a simpler data paths, and it has a loop protection. It has a limit on how many times it can read match on a packet. It was set to 4, but when we added OVN on top of it, it became clear that 4 is not enough anymore, and it got bumped to 16. This one is took a lot of time of us on this joint effort to understand these issues. They originate because by design, only TCP and UDP contract entries in established state get offloaded, and that added restrictions, constraints to the pipeline. And then we noticed that OVN had a symmetric path for RX and TX. It had mismatched zone numbers that caused these entries to never go into established state, and with that, they were never offloaded. And strictly speaking, it was an issue for the software data path as well. The zones, they weren't in a good condition. They weren't in a sync state. And also, with OVN Kubernetes, their overlay traffic was going over CT just to understand if the traffic was meant for the host or to OVN. And CT is an expensive operation. And in this case, it was really bad for offloading because it's not offloadable actually, because tunnels, they always use a fixed destination port. And with that, the reply direction never matches the original one, so it doesn't go into established state. So as it's also a heavy operation for software data path, we updated it to now match on the destination port and not rely on CT for this. Opportunity for improvement. OVN used it to do CT and then CT net. So it relied on 2 rules, on 2 flows to do the net operation. That's not needed and also not optional for both hardware and software data path. So OVN was patched in a couple of places to avoid this pattern. Now, an integration issue that we only notice when we put all the parts together. OVS and TC, this is OVS and network manager. This is a problem that has been coming and going for some.
Hi, I'm Ariel Levkovich from NVIDIA.
And hi, I'm Marcelo from Red Hat.
Today we're going to talk about OVN hardware offload. We're going to do a quick overview of why is it needed, the challenges and work we did in order to achieve full offload, and show them some performance numbers and talk about the next steps. So let's get into it. Why is it needed? So as cloud environments getting more and more bandwidth demanding, networking performance demanding with the new speeds of 200 and 400 gigs around the corner, and more complex applications such as AI, machine learning. And in addition, we also see more and more new networking features in the field of security, quality of service, and more. As they are introduced, it creates more and more complex packet forwarding paths, and the SDN enforcement by the CPU becomes more and more heavy, where the CPU service. On the right side, you will see the results with the offload compared to running without hardware offload, meaning OVS datapath. We see pretty consistent boost among the use cases. We get about 2x, a little bit over 2x performance boost. You can see three basic use cases here, pod to pod, pod to external network, and pod to a service. On the right side, you will see the results with the offload compared to running without hardware offload, meaning OVS datapath. We see pretty consistent boost among the use cases. We get about 2x, a little bit over 2x performance boost, which is quite significant, and also means the containers that usually share the CPU time with the packet forwarding services. So we get much more time for the application to run its stuff on the CPU. Those are, as I mentioned, preliminary results. We're still working on large-scale testing in larger environments and additional use cases. We're working on more than 20 different use cases of traffic forwarding within the OVN cloud. And so far, we can definitely say the results are showing and the improvement is significant. And more stuff are in the works, more improvements, and overall, it looks very promising.
All right, now back to future challenges. We have check packet larger action. There is no clear way to how to offload it. It has a new type of behavior that's not supported by TC today, because it's an action that it's at the same time an action, but also a filter. It's a match. It takes an action, and it compares the packet size, but then it jumps to different resolution ID, depends on the results, or take different actions. Some optimizations were done on OVN layer already to avoid this action when not required, like on east-west traffic, but other cases may still hit it and not get offloaded. The new DACTTL optimization on OVS kernel datapath that still has some painting patches on upstream hits the same problem, because it is doing an action to decrement the TTL and then comparing and then different actions depending on it. There's the support for matching on the original tuple, to match on the original tuples before doing that. And today this was avoided by using different logics in the flows. And there's also the problem of CI on how to make sure that further changes to OVN, OVN Kubernetes, and OpenStack neutral OVN, they won't break the offloading. So folks, this is a quick summary of our joint effort. We have been working on this for months and many months in there. And as we can see, we have improvements towards the offloading and also towards the software datapath. And it was beautiful to see how software datapath got some really nice optimizations out of the offloading effort.
Exactly, and to add to it, we realize now that while we know and already have support for various features in the offload framework, as standalone. We really need to put those features and look at things as a whole and test them in complex environments with production level workloads and configurations, because eventually we may encounter different gaps and still missing parts when trying to combine all those elements together into one complex environment. And basically this allowed us and will allow us in the future to move faster and reach the full offload with all the use cases and various packet patterns that we see.
All right. Thanks to our speakers. Before we jump into questions, I have to first apologize that at one point we had the video restart. I think I managed to reposition it so that we didn't miss much. But if we missed more than a few seconds, I'm very sorry about that. We do have a full recording of the talk on YouTube, and I will post a link to that soon here. So I believe that we have both of our presenters available to answer questions. Are you there, folks?
Yes, here.
All right, great.
This is Ariel.
Hello, Ariel. And I see that Marcelo is here as well. So we have one question posted in Q&A from Dimitrius Sierra, who asks, would it make sense to add upstream, if possible, regression tests that ensure that changes at different levels, OVN, OVS, etc., don't break these hardware offload scenarios? And that seems like a really good question to me. What are your thoughts?
I'll go ahead. Well, yeah, most definitely. And I think Marcelo mentioned it in one towards the end, one of the last slides, that one of the next steps and a major goal for us would be to achieve a working upstream CI that will basically run regression tests and ensure that offload does not get broken by new patches and new changes that can come from various contributors that not necessarily aware of hardware offload constraints and just looking at the software implementation and do not realize that, which is expected. But essentially, we want to make sure that everything is gathered in like a centralized location and getting tested, and the contributor will get a notification if he kind of hit a hard spot and affected hardware offload functionality. This is definitely something we are trying to achieve. Internally at NVIDIA, we are working on AI systems that will run those regression tests, and we are in talks on how we are looking into a possibility of actually open it to upstream and external contributors essentially. But the short answer is yes. I don't see a way we can safely move forward with new features and new implementations without having this CI system established and not getting hundreds of bugs every week about how we're offloading. Yeah.
Thank you for that that answer. One of the things that struck me about this is that there's a lot of complexity, and I wonder whether that is inherent or if it's an artifact of the design and the architecture. So I hope it tends to be more of an artifact and something that we can work on reducing over time. Let's see here. We're out of time for questions here, so unfortunately I should have given Marcelo and Ariel a chance to respond to that, but maybe they can put some of their thoughts into the chat. So our final talk of this